Hello and welcome everyone. My name is Minhaj. I'm the CEO of a company called SIDA, which is an AI-enabled research and academic solutions company. And without any ado, I don't think my guest today need an introduction. We have got Dr. Josh Starmer with us from infamous StatQuest. Welcome, Josh.
Hello. Hello. We're going to talk about neural networks today. Hip, 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 hooray. StatQuest. Hello.
Boy, did I miss that.
Yeah.
Happy New Year, Josh.
Starmer. Yeah. Happy New Year to you. Yeah.
How was it in North Carolina? Was it a snowy New Year, Christmas, or you have the regular?
It was so North Carolina is kind of, we have relatively mild winters. It gets down to maybe like 0 degrees centigrade, but it usually gets up to about 10 degrees centigrade in the daytime. And I'll be honest, it was just gloomy and rainy the entire time. We just got rain and clouds and no sun for weeks. And actually today is the first day we've had the sun in forever, and I'm just loving it.
Is it really interesting? Because I'm in the middle of the desert, and that's where we get around 2 and 4 and 5 and 10, and the days are like 15. So you're not getting a bad deal back in US, are you?
Yeah, we're just getting lots of rain. So much rain. Too much. Yeah. We have flooding. I mean, it's flooding.
Oh, really?
Streets. Yeah.
Okay.
So.
Okay.
Anyway.
How is the Christmas? Do you have this like a Santa version of this thing in your head?
No, I just have something that protects my head from flakes of cheap fabric from the headphone that is cheap. Anyways, yeah, I just wrapped this up.
Remind me to send you a good one.
That'd be great. I'd love some good headphones. Holy smokes.
Oh, it's nice. We've got Jeremy from Peru already here.
Oh, hey Peru.
Hey, Jeremy.
Yeah.
And how did your Christmas go? Got really nice gifts?
You know, yeah. What did I get? I think I got this shirt that I'm wearing.
Oh, so that was pretty
nice. Yeah, it was nice. Nice. Yeah. Cool. Do you have a good New Year's and a good holiday?
Yes. First time forever. It was a indoor kind of New Year because of COVID-19. No fireworks, no nothing. Even though we had a lot of people just go out and did some crazy stuff. But all in all, it was a quieter one.
Sounds great.
It is. Josh, you have started the neural network series now after your blockbusters. And I heard your PC got 1 million views now, not right? The video.
That's right. Yeah. Yeah, I'm really excited about that.
When did you actually record it the first time?
Like maybe 3 years ago is when so it took 3 years to get to 1 million.
Did I lose you?
Yeah, so maybe. Hooray. Sorry about that.
Okay.
I don't know what that was.
I don't know, it's me or the rain got into your internet.
Yeah. Yeah, exactly. It's all wet.
So the wonderful part, which I'm a huge fan of, is the simplicity that you put into seemingly one of the most complicated calculations in the history of computer science and statistics. And we're here to talk about something which took scientists around 50 years to make more complicated so that people can understand, and you just put it out in a way like the proverbial your grandma can understand that.
That's right.
So let's talk about your first episode,
Okay.
which came out already in August, I
Yeah.
believe, the first part of your neural network series called Inside the Black Box. So what's the black box?
The black box. So in machine learning, there are different types of methods. Like tree-based methods are pretty. You look at a tree-based method, and it's pretty obvious what it's doing, how it's separating the data and making classifications or predictions. But with neural networks, neural networks are always considered a black box because they're usually too complicated to understand. You just look at them, and you're like, I have no idea what it's doing. It's just working, or it's not working. I don't know. And so, and a lot of people just give up. They don't even try to understand what the neural network is doing because they say, well, we're just going to treat it like a black box. But it's actually possible to see and understand what neural networks are doing. And that's why I say it's inside the black box, to kind of, because that's what I'm going to do. I'm going to show you what's inside the black box. It doesn't have to be a black box anymore. It's actually not that. Everyone says it's really complicated, but it's actually not that complicated. What makes it complicated is if you have a complicated data set, and if you have a simple data set, then your neural network will end up being very simple and it's easy to understand. And you can see the concepts and you can understand how they work. So when later you've got a more complicated data set, well, maybe you can't look and see what it's doing, but you know what it's doing. You've got an intuitive sense of what's going on inside there.
Okay. Now, when you talk about biases and weights and learning rate and steps, it becomes a lot more complicated for people who are, well, let's say, not that statistically gifted. And when you talk about that, you put that in a sequence of one layer neural network in your videos.
Yeah.
So if you could just walk us through how weights and biases actually help us get to the output, and how does it actually tweak? We're going to be talking about your backpropagation soon. But first, let's talk about the weights and biases. What are they?
Okay. So yeah, you want me to just go through this StatQuest and?
Sure, go ahead.
Okay, let's do it. Bam. So this is part 1 in a series. I started this back in August, but I'm still at it. I'm just about to release 2 new videos in this series, so I don't even know what parts those are anymore. And I've actually got 3 new videos coming out. I've got one that that shows. So this StatQuest has a very simple neural network. The one I'm working on right now, it has a more complicated neural network. It's got a more complicated input and output situation, and you'll learn more about that in a second. And then ultimately I'm moving towards explaining how something called convolutional neural networks work. And convolutional neural networks are used for image recognition. So that's what's coming. And this is what we've got so far. So this is the very first part in that series. So if you're new to neural networks, this is the place to start. So neural networks are one of the most popular algorithms in machine learning, cover a broad range of concepts and techniques. However, people call them a black box because it can be hard to understand what they're doing. The goal of this series is to take a peek into the black box by breaking down each concept and technique into its components and walking through how they fit together step by step. Beep, 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 beep. In this first part, we will learn what neural networks do and how they do it. Beep, 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 boop. And then in part 2, I talk about how neural networks are fit to data with backpropagation. Beep, 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 beep. And then I talk about variations on the simple neural network presented in this part. And then I eventually talk about something called deep learning. Deep learning is what's coming out with that convolutional neural network. And that should be out by the end of this month, hopefully. Beep, 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 beep. Beep. Okay, so note, I've got some crazy awesome news. I have a new way to think about neural networks that will help beginners and seasoned experts alike gain a deep insight into what neural networks do. For example, most tutorials use cool looking but hard to understand graphs and fancy mathematical notation to represent neural networks. In contrast, I'm going to label every little thing on the neural network to make it easy to keep track of the details. And the math will be as simple as possible while still being true to the algorithm. We don't A lot of people use a fancy mathematical notation to represent neural networks, but you don't need to. It's not required. And that's I'm taking advantage of that fact to show you the same math, but just using much simpler notation. These differences will help you develop a deep understanding of what neural networks actually do. So, with that said, let's imagine we tested a drug that was designed to treat an illness. And we gave the drug to three different groups of people with three different dosages: low dosage, medium dosage, and high dosage. Now, the low dosages were not effective, so we set them to 0 on this graph. In contrast, the medium dosages were effective, so we set them to 1. And the high dosages were not effective, so those are set to 0. Now that we have the data like this, we would like to use it to predict whether or not a future dosage will be effective. However, we can't just fit a straight line to the data to make predictions, because no matter how we rotate the line, it can only accurately predict 2 of the 3 dosages. The good news is that a neural network can fit a squiggle to the data. The green squiggle is close to 0 for low dosages, close to 1 for medium dosages, and close to 0 for high dosages. And even if we have really complicated data set like this, a neural network can fit a squiggle to it. In this StatQuest, we're going to use this super simple data set and show how this neural network creates this green squiggle. But first, let's talk about what a neural network is. A neural network consists of nodes, these squares, and connections between the nodes, these arrows with numbers on them. The numbers along each connection represent parameter values that were estimated when this neural network was fit to the data. For now, just know that these parameter estimates are analogous to the slope and intercept values that we solve for when we fit a straight line to data. Likewise, a neural network starts out with unknown parameter values that are estimated when we fit the neural network to a data set using a method called backpropagation. We'll talk, or I have already done this. I talk about how backpropagation estimates these parameters in part 2 in this series. So if you're interested in that, you can check that out. But for now, just assume that we've already fit this neural network to this specific data set. And that means we have already estimated these parameters. Also, you may have noticed that the nodes have curved lines inside of them. These bent or curved lines are the building blocks for fitting a squiggle to data. The goal of this StatQuest is to show you how these identical curves can be reshaped by the parameter values and then added together to get a green squiggle that fits the data. Note, there are many common bent or curved lines that we can choose for a neural network. This specific curved line is called Soft Plus, which sounds like a brand of toilet paper. Alternatively, we could use this bent line called ReLU, which is short for rectified linear unit and sounds like a robot. Or we could use a sigmoid shape or any other bent or curved line. Oh no, it's the dreaded terminology alert. Curved or bent lines are called activation functions. When you build a neural network, you have to decide which activation function or functions you want to use. When most people teach neural networks, they use the sigmoid activation function. In practice, however, it is much more common to use the ReLU activation function or the soft plus activation function. So we use the soft plus activation function in this quest. Anyway, we'll talk more about how to choose activation functions later in this series. Note, this specific neural network is about as simple as they get. It only has one input node where we plug in the dosage, only one output node to tell us the predicted effectiveness, and only two nodes between the input and output nodes. However, in practice, neural networks are usually much fancier and have more than one input node, more than one output node, different layers of node between the inputs and output nodes, and a spider web of connections between each layer of nodes. Oh no, it's another dreaded terminology alert. The layers of nodes between the input and output nodes are called hidden layers. When you build a neural network, one of the first things you do is decide on how many hidden layers you want and how many nodes go into each hidden layer. Although there are rules of thumb for making decisions about the hidden layers, you essentially make a guess and see how well the neural network performs, adding more layers and nodes if needed. Now, even though this neural network looks fancy, it is still made from the same parts used in this simple neural network, which only has one hidden layer with two nodes. So let's learn how this neural network creates new shapes from the curved or bent lines in the hidden layer and then adds them together to get a green squiggle that fits the data. Note, to keep the math simple, let's assume that dosages go from 0 for low to 1 for high. The first thing we're going to do is plug the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. For example, the lowest dosage, 0, is multiplied by negative 34.4, and then we add 2.14. You get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which, in this case, is the soft plus function. Note, if we had chosen the sigmoid curve for the activation function, then we would plug 2.14 into the equation for the sigmoid curve. And if we had chosen the ReLU bent line for the activation function, then we would plug 2.14 into the ReLU equation. But since we're using soft plus for the activation function, we plug 2.14 into the soft plus equation. Beep. And the log of 1 plus e raised to the 2.14 power is 2.25. Note: in statistics, machine learning, and most programming languages, the log function implies the natural log, or the log base e. Anyway, the y-axis coordinate for the activation function is 2.25. So let's extend this y-axis up a little bit and put a blue dot at 2.25 for when dosage equals 0. Now, if we increase the dosage a little bit and plug 0.1 into the input, the x-axis coordinate for the activation function is negative 1.3. And the corresponding y-axis value is 0.24. Let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase the dosage values all the way to 1, which is the maximum dosage value, we get this blue curve. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1, 0 to 1, corresponds to this relatively narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, and then multiply them by negative 34.4 and add 2.14, then we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new blue curve. Bam! Now we scale the y-axis values for the blue curve by negative 1.3. For example, when dosage equals 0, the current y-axis coordinate for the blue curve is 2.25. So we multiply 2.25 by negative 1.3 and get negative 2.93. And negative 2.93 corresponds to this position on the y-axis. Likewise, we multiply all of the other y-axis coordinates on the blue curve by negative 1.3. And we end up with a new blue curve. Bam! Now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by negative 2.52 instead of negative 34.4. And we add 1.29 instead of 2.14 to get an x-axis coordinate for the activation function. Remember, these values come from fitting the neural network to the data with backpropagation. And we'll talk about that in part 2 in this series. And actually, I've already done that. So if you're interested, you can check out those videos. Now, if we plug in the lowest dosage, 0, into the neural network, then the x-axis coordinate for the activation function is 1.29. Now we plug 1.29 into the activation function to get the corresponding y-axis value and get 1.53. And that corresponds to this yellow dot. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values. And we get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1 corresponds to this narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, we only get the x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections. And that results in each node in the hidden layer using different portions of the activation functions to create these new and exciting shapes. Now, just like before, we scale the y-axis coordinates on the orange curve. Only this time, we scale by a positive number, 2.28. Beep, boop, beep, boop, beep, boop, beep. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. Beep, boop, beep. And that gives us this green squiggle. Then, finally, we subtract 0.58 from the y-axis values on the green squiggle, and we have a green squiggle that fits the data. Bam! Now, if someone comes along and says that they are using dosage equal to 0.5, we can look at the corresponding y-axis coordinate on the green squiggle and see that the dosage will be effective. Or we can solve for the y-axis coordinate by plugging dosage equals 0.5 into the neural network. And then do the math. Beep, boop, beep, beep, boop. We'll just beep, beep, boop, boop, boop. Just move through this really fast. Beep, beep, boop, beep, 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 boop. Beep, boop, boop, beep, boop. Beep, beep, boop, 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 beep, boop, beep, boop. So we have 1.03. And that's the y-axis coordinate on the green squiggle. So we see that the y-axis coordinate on the green squiggle is 1.03. And since 1.03 is closer to 1 than 0, we will conclude that a dosage equal to 0.5 is effective. Bam! Now, if you've made it this far, you may be wondering why this is called a neural network instead of a big fancy squiggle fitting machine. The reason is that way back in the 1940s and 50s, when neural networks were invented, they thought the nodes were vaguely like neurons, and the connections between the nodes were sort of like synapses. However, I think they should be called big fancy squiggle fitting machines, or BFSFMs, because that's what they do. Note, whether or not you call it a squiggle fitting machine, the parameters that we multiply are called weights. And the parameters that we add are called biases. Note, this neural network starts with two identical activation functions. But the weights and biases on the connections slice them, flip them, and stretch them into new shapes, which are then added together to get a squiggle that is entirely new. And the squiggle is shifted to fit the data. Now, if we can create this green squiggle with just two nodes in a single hidden layer, just imagine what types of green squiggles we could fit with more hidden layers and more nodes in each hidden layer. In theory, neural networks can fit a green squiggle to just about any data set, no matter how complicated. And I think that's pretty cool. Triple bam. So I think that's it for the first part of the neural network series. So thank you for your
Wow.
patience.
That was very, very informative. I think that grandma would be very proud of you. Now, a couple of questions for the very beginners. Now, people who have already seen your videos on statistics and machine learning concepts, you have explained in detail support vector machines, random forests, decision trees, and other machine learning algorithms. Why do we need neural networks in the first place if we already have algorithms like that? That is way more complicated than our simple regression equations of y is equal to mx plus b. Why make our lives more complicated than they already are?
So early in the StatQuest, I tried to illustrate why a neural network would be helpful as opposed to linear regression. I love linear regression. Don't get me wrong, but linear regression can only fit a line or a flat surface to things. If we got multiple dimensions in our linear regression, so we got multiple variables or whatever, everything has to be flat or linear. In contrast, neural networks can fit, obviously you see, can fit squiggles to data. It doesn't just have to be a straight line or a flat surface. It can be a squiggle or a crinkled up surface that's kind of, all kinds of shapes to it. And that allows us to capture sort of what we call non-linearities or sort of even, what do they call, interaction effects between different variables. We can capture those with a neural network. Why would we want to, when we have something as fancy? So there are fancy things like XGBoost and support vector machines that can also model those same things. They can model the non-linearities and the interaction effects between the variables. Why would we also want to use neural networks? Well, one reason is it's nice to have a bunch of tools to solve problems that can be complicated. Not every nonlinear interaction-based problem can be successfully, optimally solved with XGBoost or support vector machines. And so it's nice to have another tool that we can try to see if it works. And so that's one reason why it's nice to have another tool. Another thing that's nice about neural networks is they can be extended quite readily to do sort of high speed image recognition. And like I said, I'm in the future StatQuest, probably by the end of this month, January 2021, I should have my StatQuest on convolutional neural networks, aka deep learning, to show you how they can easily be used for doing image classification. And that's a very useful thing to do these days with machine learning.
Very interesting. Now, Josh, let's talk a little bit about, before we actually go to your second part, backpropagation and more maths. Let's keep it fun for people and tell them what it actually can do, not in terms of only data. There's an OpenAI SoundCloud channel on which, using these neural networks, they have composed music totally generated by these neural networks that has mixed the classical musicians like Bach and Mozart and Pachelbel and other people. And then we have self-driving cars and the application in healthcare. We're going to be talking about one of your papers that I found really interesting also. So tell our viewers how are neural networks more than just a fancy name, and what are the real contributions that it can actually make in human lives?
I mean, yeah, neural networks are used for all kinds of stuff, like the things you were just mentioning. all of the self-driving car stuff is based on neural networks. Although I will say, I'm a little skeptical that a neural network alone will solve that problem. Just because, as you saw in that, actually, I can show this to you. This is a good illustration of like maybe one of the weaknesses in neural networks.
Yes, and I think maybe
scroll back.
sure. I've just added the stream.
So
just go ahead, and I'll ask afterwards.
Yeah. So if you can see, if you see the green squiggle, okay, it fits the data, but not perfectly, right? And it's got this bulge right in between these two groups of values. So we've got the low dosage group here and the high dosage group or excuse me, the moderate or the medium dosage group right here. But you see, we've got this bulge. So one thing that's difficult to predict with neural networks is how the squiggle or the crinkled surface or whatever it is going to be shaped in between observed data points. So it might make more sense to us to have a more snugly fitting bell-shaped curve here. But a neural network's like, well, I don't have data in that region. It doesn't really matter. I don't get penalized if I'm close or far from anything, because there's just no data to compare how well the green squiggle fits. And so one thing that's weird about neural networks is for values that are in between what you've trained it on, you don't really know what you're going to get unless you can draw it out like this. And this is a very simple example. But if we had more variables and more output, more input variables and more output values, we would no longer be able to draw this squiggle, and we would just be like, well, I actually don't know what it does in between. And I think that, to be honest, I think that's one of the problems. And I'll be honest, I'm no expert on neural networks and self-driving, but that's one of the things that I think needs to be addressed with using a neural network for self-driving a car, because it's, there's a lot of things that happen all the time, but the thing that people are pretty good at is reacting to situations they've never seen before and going, I don't know what's going on. I'm just going to slow down and pull over, or I've never seen this before, but if I just move to the left, I will avoid this problem. I think a neural network might have a little more difficulty knowing what to do in between sort of observed experiences. So that's that's something I'm a little skeptical about. That being said, I'm no expert on that field, so I could be totally wrong, and maybe they figured that out. But to give like I said, another thing that neural networks are used for all the time is image classification. So like on your cell phone, if you take a bunch of pictures of your friends, your phone will will start learning who your friends are, because it'll look at those pictures and go, hey, that's Minaj. That's you're Josh, and the phone can figure that out. And that's all sort of what's called convolutional neural networks doing that, sort of figuring that out. And that's useful for organizing my photos.
Well, it sounds very futuristic. For example, I saw this video by Chris Brown, which is a influencer in tech, and then he took a car, self-driving car by a company called Yandex. I think it was CES last year, or was it this year? Probably not this year. And then there is a driver sitting just beside the steering wheel to press the kill button if there's something, but otherwise it will just take you around LA, and we simply put in the destination and it will take you there. But I'm just wondering if it's all running through high power GPUs by NVIDIA, and it has seen those roads and those maps many times, very little changes. But what happens if all of a sudden a beaver comes from somewhere, or a bird appears, something that the neural network has never seen before?
Yeah.
Is that a risk that you're willing to take? Would you take a self-driving car, Josh?
I'll be honest. I will not be the first person in a self-driving car. I mean, if it's on a closed course and we're driving at relatively low speeds, but if we're going 80 miles an hour actually 80 miles down an hour down an interstate is relatively easy to it's relatively easy to program, because on an interstate, which are these long roads that are between cities and between major areas, there's not a lot going on. And usually the lanes are separated. So everyone going this way, we're all together in our lanes, and there's nobody coming at us. And there's usually fences and whatnot to keep animals from going in the way. That's actually something that would be relatively easy to code. It's when you're in a city and there's like people on bikes and there's people walking and there's animals and there's all kinds of stuff. That's the thing when I start getting a little nervous about how it's going to react, because there's just a lot of variety that can happen and you just never know. I mean, could be that something falls off of the truck in front of you. I've seen that happen before, and what is the car going to do? I don't know. Hopefully it'll stop. But I want to put a star next to everything I say. I'm no expert in the field, and like I said, people may have already figured out these problems, and they've got like a default like way of detecting anomalies or things that are out of the range of the training data set. And maybe as soon as they recognize that's the situation, the car just pulls over and stops, or maybe it does something like that.
Yeah, well, that's for the animal. What about birds? Because if you've taken a flight, on airport, they have people going around and firing some shots so the birds just go away and they don't actually cross the path with the planes. What if that situation happened with cars? Because there's certainly no way on the highway to keep the birds out of the way. And what if the car detects that that's something that is dangerous, and it presses the kill switch, and then it stops right in the middle of highway, and there's a car coming 80 miles per hour behind that?
Yeah,
not a risk I'm willing to take.
That'd be a disaster. Well, let's hope that doesn't happen.
I hope so. I don't know why Tesla stock is going out of the bounds, even with all those things that can happen.
Yeah, yeah, I think. Well, that's a whole nother topic. But to be honest, I think their autopilot is a small part of what sells their car. It's a cool idea, but what sells their car and allows for a lot of growth is the battery nature of it, the electric nature of it. And I'll be honest, I have driven a Tesla before. It was super fun. They are really fun to drive.
Okay, and I hear it's pretty expensive also. What's the lowest of the line model price? I think it's north of 75K, no?
No, the Model 3, at least in the United States, retails for 35,000. So it's about half the top end. I've never driven the Model S. That's the more expensive sports car.
Mhm.
I've only driven the Model 3, which is the sort of what they call the cheap one. It's still expensive, right? $35,000 is a lot of money. But I had a friend of mine at UNC. They bought one, and it let me drive it around, and it was a blast.
Nice. In what way? It was speed, or it was just like smoothness, or luxury?
Oh,
What was that?
every single thing. They're fun to drive. Like, they accelerate really quickly. They're very responsive to the road. So in a way that a combustion engine isn't responsive, in that a combustion engine, you're always having to build up pressure uh, in things to speed things up and move things. In an electric guitar, it's not electric car, not guitar, but in an electric car, it's instantaneous. You touch the pedal and you go. There's no lag time when you're building up pressure in the whole network of the engine. So that's fun. But the other thing that's fun about it is the car itself is like amazing. In the Model 3, they got this big screen, and it's awesome. They've got radars and I don't know what they have all around the car that can tell you where all of the other vehicles and whatnot are within, near you. I didn't use autopilot. I did use its adaptive cruise control, which is and lane steering thing. So I let go of the handlebar on the interstate, and I let it take care of the pedals and the steering wheel. And it was amazing. It worked great. So in certain situations, it's just fantastic and very fun and very futuristic. It's sort of like the iPhone of cars. There's nothing else out there that's like it.
So we have a question by Yash. Did you try it up the hill?
Yeah, I mean, I drove up a hill. Yeah, it was awesome. It just went lickety split straight up the hill. I mean, it's got plenty of power. In fact, they have a race in Colorado. There's a mountain called Pikes Peak, and it's a very tall mountain. I don't know if it's the tallest one in Colorado, but it's a tall mountain. But there's a road that goes all the way to the very top of it, and they have a race there. And it used to be they'd have combustion engine cars, because that's what all the cars were. But they had to make a separate category for electric cars because electric cars can actually do it faster. It's like how they have different age groups for competing or something like that. It's like combustion engines are in the old, they're like the senior citizens on the road in terms of speed and performance compared to the electric cars. They perform much better.
I think I already saw a video on YouTube where Tesla was racing with a Ferrari, and I guess the disadvantage of having a combustion engine from going to 0 to 100 is that it does take this initial lag, and electric car doesn't have that, and I think Tesla beat it like easily.
Yeah. Even the Model 3, which is the cheap model, or cheap, we'll put that in quotes. It's still pricey. $35,000 is still a lot of money. But compared that to a Ferrari, which I don't know how much a Ferrari costs, but it costs a lot more than $35,000. That Model 3 is, I mean, you feel that when you start accelerating, you feel it. I mean, you don't have to accelerate that fast. It's just fun to do. Yeah, it's pretty awesome. I highly recommend it.
Sweet. If you have $35,000, that is.
I know, exactly. I don't, but if someone wants to give me one, that'd be awesome.
Yeah, well, wait till a million subscriber and someone might actually get you that.
Yeah.
Let's get back to the more mathematical portion about backpropagation. So I do understand, you add weights to your initial inputs, and then you add biases, and then you apply a function, activation function, ReLU, softmax, 10H, sigmoid, anything you want. And then it goes to the next layer, and then it gets to your outputs. Yeah. Now, what if the output is not what we wanted when we put in the input? What do we do now, Josh?
We use backpropagation.
Nice. And what is that?
Yeah. I'll share that with you. Give me just 1 second.
Sure.
Give me just 1 second. I gotta pull up that StatQuest. Yeah, let's do an exposure to backpropagation.
Well, I think the name sounds cool.
Definitely, right? Sounds totally awesome. So here's this. Now let me just share my screen. Share my screen. Boom. There it is. So let's talk about backpropagation. This is the main ideas behind backpropagation. I actually have 2 follow-up videos that dive into the details of like every single thing. But we're just going to focus on the main ideas of how neural networks are trained and fit to data. So in the last thing we did, we started with a really simple data set that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Then we talked about how a neural network like this one fits a green squiggle to this data set. Remember, the neural network starts with identical activation functions. But using different weights and biases on the connections, it flips and stretches the activation functions into new shapes, which are then added together to get a squiggle that is shifted to fit the data. However, we did not talk about how to estimate the weights and biases. So let's talk about how backpropagation optimizes the weights and biases in this and other neural networks. Boop, boop, boop. Note, backpropagation is relatively simple, but there are a ton of details, so I've split it up into bite-sized pieces. In this part, which is what we're doing right now, we're going to talk about the main ideas of backpropagation. That means we're going to talk about using the chain rule to calculate derivatives. Beep, boop, beep, boop, beep. And then we're going to talk about plugging the derivatives into an algorithm called gradient descent to optimize parameters. Beep, beep, beep. In the next part, we'll talk about how the chain rule and gradient descent apply to multiple parameters simultaneously, and we're going to introduce some fancy notation. Then we go completely bonkers with the chain rule and show how to optimize all 7 parameters simultaneously in this neural network. Damn. So first, so we can be clear about which specific weights we're talking about, let's give each one a name. So that's going to be weight 1 or weight sub 1. That's weight sub 2. That's weight sub 3. That's weight sub 4. And let's give each bias a name. That's bias sub 1. Remember, weights are multiplied and biases are added. So we've got bias or B sub 2 and B sub 3. Note, conceptually, backpropagation starts with the last parameter and works its way backwards to estimate all of the other parameters. However, we can discuss all of the main ideas behind backpropagation by just estimating the last bias, B sub 3. Boop. And in the next StatQuest, we'll see how these main ideas can be applied to estimate all of the other parameters simultaneously. So in order to start from the back, let's assume we already have optimal values for all of the parameters, except for the last bias term, B sub 3. Also note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. Now, if we run dosages from 0 to 1 through the connection to the top node in the hidden layer, we get x-axis coordinates for the activation function that are all inside this red box. And when we plug the x-axis coordinates into the activation function, which in this example is the soft plus activation function, we get the corresponding y-axis coordinates in this blue curve. Then we multiply the y-axis coordinates on the blue curve by negative 1.22, boop, 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 and we get the final blue curve. Bam! Now if we run dosages from 0 to 1 through the connection to the bottom node in the hidden layer, then we get x-axis coordinates inside this red box. And now we plug those x-axis coordinates into the activation function to get the corresponding y-axis coordinates for this orange curve. Then we multiply the y-axis coordinates on the orange curve by negative 2.3. Boop, 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 boop. And we end up with this final orange curve. Bam! Now we add the blue and orange curves together. Boop, 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 boop. Get this green squiggle. Now we are ready to add the final bias, B sub 3, to the green squiggle. Because we don't yet know the optimal value for B sub 3, we have to give it an initial value. And because bias terms are frequently initialized to 0, we will set B sub 3 equal to 0. Now, adding 0 to all of the y-axis coordinates on the green squiggle leaves it right where it is. However, that means the green squiggle is pretty far from the data we observed. We can quantify how good the green squiggle fits the data by calculating the sum of the squared residuals. A residual is the difference between the observed and predicted values. For example, this residual is the observed value 0 minus the predicted value from the green squiggle, negative 2.6. This residual is the observed value 1 minus the predicted value from the green squiggle, negative 1.61. Lastly, this residual is the observed value 0 minus the predicted value from the green squiggle, negative 2.61. Now we square each residual and add them all together to get 20.4 for the sum of the squared residuals. So when b sub 3 equals 0, the sum of the squared residuals equals 20.4. And that corresponds to this location on this graph. Excuse me. That has the sum of the squared residuals on the y-axis and the bias b sub 3 on the x-axis. Now, if we increase b sub 3 to 1, then we add 1 to the y-axis coordinates on the green squiggle and shift the green squiggle up 1. And we end up with shorter residuals. When we do the math, the sum of the squared residuals equals 7.8. And that corresponds to this point on our graph. If we increase b sub 3 to 2, then the sum of the squared residuals equals 1.11. And if we increase b sub 3 to 3, then the sum of the squared residuals equals 0.46. And if we had time to plug in tons of values for b sub 3, we would get this pink curve. And we could find the lowest point, which corresponds to the value for b sub 3 that results in the lowest sum of the squared residuals here. However, instead of plugging in tons of values to find the lowest point in the pink curve, we use gradient descent to find it relatively quickly. Beep, beep, boop. And that means we need to find the derivative of the sum of the squared residuals with respect to b sub 3. Note, if you're not familiar with gradient descent, you should still be able to follow what's going on in this video. However, if you want details, I have a video, a StatQuest, on gradient descent specifically. So you can always watch that to get yourself up to speed. Now remember, the sum of the squared residuals equals the first residual squared plus all of the other residuals squared. Or all of the other squared residuals. It's a more accurate way to say it. Now, because this equation takes up a lot of space, we could make it smaller by using summation notation. The Greek symbol, sigma, tells us to sum things together. And I is an index for the observed and predicted values that starts at 1. And the index goes from 1 to the number of values n, which in this case is set to 3. So when I equals 1, we're talking about the first residual. When I equals 2, we're talking about the second residual. And when I equals 3, we're talking about the third residual. Now let's talk a little bit more about the predicted values. Each predicted value comes from the green squiggle. And the green squiggle comes from the last part of the neural network. In other words, the green squiggle is the sum of the blue and orange curves plus b sub 3. Now remember, we want to use gradient descent to optimize B sub 3. And that means we need to take the derivative of the sum of the squared residuals with respect to B sub 3. And because the sum of the squared residuals are linked to B sub 3 by the predicted values, we can use the chain rule to solve for the derivative of the sum of the squared residuals with respect to B sub 3. Note, if you're not familiar with the chain rule, there's a StatQuest on that as well, and it goes through this step by step. So you'll you'll understand all the details of what's going on here. That being said, I hope I move slow enough that you're able to still follow along. The chain rule says that the derivative of the sum of the squared residuals with respect to B sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to B sub 3. Now, before we calculate the derivative of the sum of the squared residuals with respect to the predicted values, let's clean up our workspace and move these equations out of the way. Now we can solve for the derivative of the sum of the squared residuals with respect to the predicted values by first substituting in the equation and then use the chain rule to move the square to the front and then we multiply that by the derivative of the stuff inside the parentheses with respect to the predicted values. That gives us -1. And if that went too quickly for you, don't worry. You can watch the StatQuest on the chain rule and it'll go through exactly what's going on and you will understand it for sure. Anyways, we plug in times -1. Now we simplify by multiplying the 2 by -1. And we have the derivative of the sum of the squared residuals with respect to the predicted values. So let's move that up here. And now we are done with the first part. Now let's solve for the second part, the derivative of the predicted values with respect to B sub 3. We start by plugging in the equation for the predicted values. Remember, the blue and orange curves were created before we got to B sub 3. So the derivative of the blue curve with respect to B sub 3 is 0, because the blue curve is independent of B sub 3. And the derivative of the orange curve with respect to B sub 3 is also 0. Lastly, the derivative of B sub 3 with respect to B sub 3 is 1. Now we add everything up. The derivative of the predicted values with respect to B sub 3 is 1. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by 1. Note, this times 1 part in the equation doesn't do anything. But I'm leaving it in to remind us that the derivative of the sum of the squared residuals with respect to B sub 3 consists of 2 parts. The derivative of the sum of the squared residuals with respect to the predicted values and the derivative of the predicted values with respect to B sub 3. Bam! At long last, we have the derivative of the sum of the squared residuals with respect to B sub 3. And that means we can plug this derivative into gradient descent to find the optimal value for B sub 3. Let's move this equation up. Oh, by the way, just to remind you, we're going to go through gradient descent here, but if you want more details, there's a whole video on gradient descent that you can watch at your leisure. Anyways, we're moving this equation up, and we're going to show how we can use this equation with gradient descent. Oh, that's this little ad. Note, if you're not familiar with gradient descent, check out the quest. The link is in the description below. It's not in the description below yet. Maybe Minaj will put it there, but it doesn't matter. You can just check it out on statquest.org or just Google it. Anyway, first we expand the summation. Then we plug in the observed values and the values predicted by the green squiggle. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. So we plug in input equals 0 for the first point and do the math, and we get negative 2.6. Bam. Plug in 0.5 for the second point, do the math, and get negative 1.6. And then plug in 1 for the final point, do the math, and get negative 2.61. Now we just do the math and get negative 15.7. And that corresponds to the slope for when b sub 3 equals 0. Now we plug the slope into the gradient descent equation for step size. And in this example, we'll set the learning rate to 0.1. And that means the step size is negative 1.57. Now we use the step size to calculate the new value for b sub 3 by plugging in the current value for b sub 3 and the step size, negative 1.57. And the new value for b sub 3 is 1.57. So we plug that into the neural network. Changing b sub 3 to 1.57 shifts the green squiggle up, and that shrinks the residuals. Now, plugging in the new predicted values and doing the math gives us negative 6.26, which corresponds to the slope when b sub 3 equals 1.57. Then we calculate the step size and the new value for b sub 3, which is 2.19. We plug that in to the neural network. Changing b sub 3 to 2.19 shifts the green squiggle up even further, and that shrinks the residuals even more. Now we just keep taking steps until the step size is close to 0. And because the step size is close to 0 when b sub 3 equals 2.61, we decide that 2.61 is the optimal value for b sub 3. Double bam! So the main ideas for backpropagation are that when the parameter is unknown, like b sub 3, we use the chain rule to calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case was b sub 3. Then we initialize the unknown parameter with a number. In this case, we set b sub 3 equal to 0. And used gradient descent to optimize the unknown parameter. Triple bam. All right. Those are the main ideas of how backpropagation works. And like I said, there are 2 follow-up stat quests that go through the nitty-gritty details of optimizing every single parameter in that neural network. So you'll get to see a whole lot of chain rule.
Wow. You have already started this neural network series back in August, and it's taking you forever to actually make that. I think it was like 4 or 5 months now that you're in the line.
Yeah. Yeah, unfortunately, I'm an incredibly slow. I mean, I work hard, but it's just very slow. One thing you don't always appreciate in the stat quest is how many drafts I have to go through to end up with a very simple example that I can illustrate. And I go through many drafts of the illustration themselves, trying to find the one that's clearest and the easiest one to see, and you can get the most information out of. So a lot of what I do is writing and then rewriting and then rewriting and then rewriting. It takes a lot of revisions to get a StatQuest from its sort of rough draft state to its final state, where I've changed all the graphics and I've changed all of the examples and things like that. So a lot of work goes behind the scenes to make it as simple as possible.
I can only imagine, because on a spectrum, there are like two extremes. One is the computer vision course at Stanford by Fei Li, which is totally for engineers. And, it takes me months to even understand the basic gradient rules and Markov chains and everything else. And then we have got some other visualized videos and neural networks. I believe if you're familiar with work of the guy from Khan Academy with 3 Blue 1 Brown series on neural networks, been viewed 8 million times. So season 3 is really interesting, but the graphics that he is actually used is definitely taking help of someone who's doing it for him, or a studio, or maybe he does it himself. But a lot of work actually goes into that, and you do it still on your own. The question is, how do you actually manage the trade-off between keeping the simplicity and conveying all the maths that goes into the neural network? That actually really fascinates me, because it'll still take me some time to actually think about ways in which I could explain that to other people, even though I understand that.
Yeah. I'll be honest, for neural networks, it was very hard. I watched, so I'll be honest, I'm not certain, but I believe 3 Blue 1 Brown does his own. I think he wrote the program in Python to do his own graphics. That guy's hardcore, and he does an awesome job. And I watched, people were asking me for years to do neural networks, and I watched his videos on neural networks. I'll be honest, I usually don't watch other YouTubers at all. And the reason why I don't watch them is I don't want to copy them. I'm afraid if I see an explanation that's really good, I'll be like very tempted to copy that person. And I don't want to do that. I want to have, if they have a great solution. And I watched, so what happened with 3 Blue 1 Brown is I looked at his videos and I go, this is perfect. Why would anyone need to add to this? And it was maybe a year later that someone wrote me and they said, will you teach neural networks? And I said, I don't need to teach neural networks. Look at 3 Blue 1 Brown, watch his videos and you will understand. And they said, I watched it and I didn't get it. And I didn't understand. And I thought, well, then maybe I need to do something. That means we need to do a StatQuest on it. And so I watched his videos again, and I realized that the graphics are awesome and he's got all the math there, but you still have no sense of what's really going on. It's still sort of like hocus pocusy black box of sure, we've got this data and we've got these equations, and then it just works. And so and I think that's fine, and that's the way a lot of people explain it, but I wanted to actually see how it worked. I wanted to understand what are the main ideas behind neural networks, and not just like how to make neural networks work. I wanted to be able to visualize it. I'm what they call a visual learner. And so I have to see things for me to understand them. And what was missing in the 3 Blue 1 Brown was the step-by-step moving the data through the neural network and seeing one step at a time exactly what's happening, how we're building those, we're taking those activation functions and we're making new shapes with them, and then how we add those new shapes together to get that final green squiggle. That, to me, like once I saw that, I was like, oh, I get neural networks now. But it took me, to be honest, it took me years to develop that intuition and understanding. That was very hard for me. It's not something that I just do instinctively. I had to struggle with that one for a long time before I made my first video. And once I made the first video, things moved relatively quickly because I wasn't on the scale of years anymore. I was on the scale of months. And so I was able to generate some new videos. And like I said, hopefully I'll have 3 more videos plus a webinar on how to do them in a practical setting in the next month or 2.
I think it's a very good segue for the question that I wanted to ask about neural networks. In your previous StatQuest on statistics and machine learning, you have used both R and Python to actually implement those algorithms that you have taught. First the concepts and then how to implement that. Do you actually plan to do that for neural networks also, where we actually get to see maybe in TensorFlow or PyTorch? By the way, that's a hot question also, which one would you pick? And then if you did, would you implement simple neural networks for people to actually get started? Or are there any resources at the moment that you would recommend?
Yeah. So what I'm going to do for neural networks is I'm going to probably do a couple of webinars. One, I just want to do basic webinars. Basic neural networks. Nothing fancy. Something that can easily just run natively in R or a Jupyter notebook. So we'll just put those together really, and we'll do a webinar of just like how to get them going, because it's nice to get these like toy ones going so that you can play with them, and you can without any nothing fancy, no big overhead. And then what I want to do is then do a follow-up where we implement a complicated neural network with a really complicated data set, a large data set, and we could try to run it with some of those fancy APIs or ways of running neural networks on big cluster computers. I want to do that eventually, but we'll probably do it in steps, where we'll start with a very simple example of how to do it in Python, how to do it in R, and then we'll move on to the more complicated data sets.
Interesting. I think if that might help. I mean, you're a visual learner. One of the good things that at least I believe in my experience, is that when people send me messages on LinkedIn and Facebook asking about where do we get started, what are the resources, sure, to get the concepts, your videos are the ones, and other courses that I recommend them. But then, doing some visual projects actually, get you determined to do that. So if I can actually share, there's something for everyone that might be interesting. There's something in neural networks that we called GAN, the Generative Adversarial Networks. It's a part of computer vision network. And I was just playing with that, and I just generated some random images where computer is generating it by itself, and then it morphs into one image from another image. So I just wanted to share just a quick output of what I could actually see when I ended with the results. So
sure,
that's a video that I actually exported.
Okay.
After I generated and see how it morphs actually.
So
it goes into another picture and the hair and style.
That's very cool. Look at that.
It's really interesting.
Wow. Oh, that's so
and
cool.
It takes very little time to actually make these projects, and it could be a very good addition for your portfolios if you're applying for data science jobs, if you're looking for internships. These are the projects that would really help you get started.
Yeah, for sure.
Now, one of the things that I wanted to ask you about, Josh, and by the way, did you answer the question about PyTorch or TensorFlow?
Oh, which is my favorite? I don't know. I don't have strong feelings, to be honest.
Okay, you're the R guy.
I do some Python too.
Okay, well, that's the consolation prize, right? Okay. Now, one of the interesting things that you have started lately, and I don't know how do you feel about that, but I absolutely dig it, which is that you made a StatQuest, or shall we call a video about the high school U.S. population sample competition.
Yeah.
And that's something I'm really interested as a Debonair participant in Kaggle, which is, by the way, the largest data science community. I thought, I should just go out and see, how do I stack up with other more cool people. And it was really interesting. It gets you the adrenaline rush and see, how am I doing with the models and everything else. And I think encouraging high school students to think in terms of data and numbers and the story out of it is very interesting.
Yeah.
And through that, I also found out that you live in a pretty nice county where you could actually afford Tesla. It's around 74K median income, which is higher than the whole state?
I can't afford it, but other people can. There are a lot of Teslas
Okay.
in my town, but I can't afford one of those.
Really. So and you have higher female percentage in comparison to other states, I guess.
It was within the county. We have a larger number of females, and I think that's driven. So in the part of the state I live in, we have the University of North Carolina, and I think that is skewed. I think more women go to universities than
Yeah.
men. Men often will not go to university at all, though they might go to a technical school or they might start a trade, like become an auto mechanic or something like that. Those are more common where I live for men to do those things, and so more women go to the university, and that skews the overall population balance to be more women.
But it still does not actually had an effect on the median income. If you could just tell us a little bit
That's
about
right.
that
Yeah.
question, and why do you think that happens?
So that was so in this video, what I did is I was looking at, we just had the US Census here. And this data that we have is not the most recent data, but it's a very cool tool that you can use. And as soon as that new census data is available, we'll be able to access that. And it's kind of cool. So anywhere in the United States, you can pull up all kinds of information about who lives there, and how much money they make in general, and what how expensive are the houses and things like that, and what kind of jobs are available and what people are doing, and who do people move there or do they move away from there. You could get all this information. And so what I did is I was like, well, I'm kind of curious about the town that I lived, and I live in Orange County, North Carolina, or Chapel Hill, North Carolina, to be specific. And so I was very curious about that. And what I noticed was that there was more women in Orange County, North Carolina, and than the state average. And not only do we have more women, we have a slightly higher median income. And so I was wondering, does that skew if you go to another county and they have more women than men? Do they also make more money than a county that has more men than women? And I was able to use census data to that was the question I had, and I was able to use census data to answer that question. The answer is no. It does the balance of or imbalance of genders, or men versus women, does not correlate with changes in the median income level for an area. But it was kind of an interesting question. It was a fun resource because you just pull it up and you're like, huh. I mean, it's just questions jump out at you, and you're like, oh, I wonder about this, and it's kind of like Wikipedia. You can kind of like answer those questions relatively easily. So that was kind of a fun example of how to tell a story with data.
It was very interesting, actually, because all other data sets, despite the popular narrative, is that women tend to not participate in STEM as much, and also the jobs that they do does not actually pay as much as the jobs that men do, because highest paying jobs.
Uh-oh. Did we just lose the connection? Hello? Are you guys still with me? I see myself. Maybe I'll play some ukulele. Hello? Are we connected? There was a weird pause. Maybe I'll use the chat and say, is there anyone here? Hello? Are you there?
Did I lose you?
You're back. Yeah, I don't know what happened there. I just
Okay.
play a little ukulele.
Yeah, I was just saying that the data is very clear that there's absolutely no bias when it comes to the wage gap. It's just like the choices, and I don't think that we can do much about that.
Well, I don't know. Yeah, that's I'll be honest, that's a question that's way out of my
Expertise.
expertise. I was just looking at the data and I noticed that there are more women in my town than men, and this town makes median income is slightly higher than other towns in the state. And so I was just sort of exploring that and trying to figure out what's going on.
Okay. Josh, there's a paper that you wrote, which is of particular interest to me, about the linkages of probable genes with the ASD. And and I find it really interesting. If you were to approach that paper, that by the way already got published in Nature, I can get better than that. But then if you were to use neural networks, how would you actually use it for the study if you were to do it again?
Yeah, so that's a good question. What is the answer to that?
I mean, it talks about the transcription of long genes, which is linked to autism. And then, interestingly, many high confidence ASD candidate genes are exceptionally long, and they're reduced in expression after top one inhibition. So your findings suggested in that paper that the chemical genetic mutation that impair that could commonly contribute to ASD and other neurodevelopment disorders. And I was wondering if you're onto something here, if we have large scale data for that.
Oh yeah. So yeah. One thing that's one thing that's kind of very useful with machine learning and so I used to work in a genetics department, and so we did a lot of work with genetic data sets. One thing that's awesome about machine learning is that we can use it to generate new hypotheses. So oftentimes, it used to be back in the day, when we do an experiment, we get very little data. We would just get the one thing we were looking for. But now we can, when we do an experiment or if someone in the lab, they can generate just tons and tons of data. And that makes it hard to sift through. I mean, they may have a specific hypothesis about a specific gene, but they're getting data for all 22,000 genes in the human genome or all 18,000 genes in a mouse genome or something like that. In machine learning, neural networks, or you could even use naive Bayes. I actually recently did a seminar for the people at UNC on how to use naive Bayes to analyze what's called genomic data. And that's data that comes from the entire genome, and how we can use that to identify new things that might be associated with this disease. So in this case, in this paper, we were looking at autism spectrum disorder. And we could use machine learning, like nowadays, we could use machine learning as a way to try to identify other genes or other sort of modifications to the genome that are associated with ASD, and we could use the machine learning as sort of a hypothesis generation tool, which I think is awesome. So in that respect, I think of machine learning as sort of the 21st century microscope for molecular biology. It's because the data we get from molecular biology, it's no longer like an image on a slide. It's actually like a 1 terabyte size file. And you can't just stare very closely at a 1 terabyte size file, but you can run a machine learning algorithm on that huge file, and it can pop out interesting stuff and point it out to you. So that's something that would be different today versus, when I originally worked on that paper.
And do you think you would have gotten better accuracy with neural networks?
So it's sort of like apples and oranges, to be honest. So in this manuscript, we were taking the approach of sort of analyzing the activity of this specific topoisomerase, which is is that right? Topoisomerase, with this specific enzyme that, oh, geez, it's been a while. Anyways, we were interested in very specific things, and so the analysis that I did in this manuscript was driven by statistics and sort of trying to evaluate, can we find a signal in this data, and if we can find a signal in this data, how confident are we in that signal? Which is a slightly different problem than, say, a machine learning problem. A machine learning problem is like, we found a signal, we're gonna apply that signal to this data set and see if we can find other things with similar signals. That's a slightly different problem to deal with, and so it's sort of like comparing apples and oranges. I don't really know if a neural network would have improved this specific data analysis or not. It just sort of was what it was.
Okay. We have one question here, which is, the lectures on StatQuest about backpropagation neural networks have hands-on examples. That's something that I asked you earlier, that if you were ever going to release a notebook or something.
That's exactly right. So we don't have hands-on examples yet, but it is my goal is to have hands-on examples, hopefully in the next month or two. I'll work as fast as I can, as hard as I can. It'll be ready when it's ready. That's, unfortunately, it's out of my control. I just work as hard as I can, and things are done when they're done.
Well, best strategy to do productive work, I guess.
Yeah, exactly.
Now, Josh, we have held you for quite some time now. We'll just end with a rapid fire round. What's your favorite food?
Oh, geez. I love food. So it's hard to say.
To eat or to cook?
All of the above. I love cooking. In fact, you'll even, if you dig deep enough in StatQuest, you'll find cooking videos. I can't answer that question. I love, everywhere I go, I just love eating whatever the food is they have there. I just love eating, and I love cooking, and I just love food. So I don't really have a favorite.
I think I noticed about you is that before a computer science bachelor, you have another bachelor's in musical theory.
Yeah.
Did you really want to become a musician?
I did. Yeah. In fact, and I did spend some time as a professional musician. A lot of people think that I sing silly songs. Actually, I love those silly songs, and they actually serve a purpose in the StatQuest, and that they help people realize that data analysis, it's not that big a deal. Whatever, we got a silly song, and so you may not have a great exposure to sort of my deep passion of music, but I've actually composed music for movies. One of those movies made it to the Cannes Film Festival in France. I've written music for ballet companies. I've written music for myself. I've written music for television commercials. So I've done a lot of stuff with music, and music is fun. I'm very passionate about it, and I love it, and it's a great thing to do. But I'll be honest, my number one love right now is StatQuest. And the reason why I love StatQuest so much, I'll tell you. Music is great, and I love music, but when I write music, people are always saying, I used to write films soundtracks, and people would say, yeah, this is, the music you wrote was great, but could you make it sound more like this? And they would say, they'd give me some example music. And I'd go, sure, I can make it sound a little bit more like that. And so I'd tweak it and make it sound a little bit more like that. But what they really wanted wasn't necessarily for it to sound a little bit more like that, but to sound a lot more like that. Basically, they wanted me to copy that, but make enough changes that they couldn't be sued for copyright infringement. And that's fine, but that's not very interesting for me. I mean, you could get anyone to write music that sounds just like something else. I don't necessarily want to just spend the rest of my life copying what other people do and then tweaking it enough so that we don't get sued. What I want to do is I want to write the music that I want to write. And I want to play the music that I want to play. And so music is, to really make money in music, you're kind of like constantly trying to make music that other people want. And that's, that's fine, but not really for me. What I love about StatQuest is nobody ever tells me to make a StatQuest like somebody else's video. Nobody says that StatQuest is good, but it would be better if you made it more like this guy or this other video that I saw on neural networks. Everybody says, to me at least, they say, you know what I like about StatQuest? I like that it's different from everything, and and what I like about StatQuest personally is that it's my own vision, it's my own way of thinking about it, but it's useful and people want it for what it is. And so, in a respect, in a way, StatQuest is a more pure expression of my personality and who I am and the way I see the world than music ever was. So yeah, I prefer to make StatQuest these days over music.
I remember the analogy that it's like home. Your home might be smaller and not as nice as other people, but it's still home and it's yours, and you can do whatever you want to do with it.
Exactly.
Nice. Now, the tragedy of my life is that, I would rather play ukulele if there was an easier way to play F chord. On my guitar, I've never mastered that. I mean, how do you actually do that on ukulele? Is it a lot easier?
Only 4 strings. And so you can play a chord with just one finger.
2 frets together?
Yeah, there's frets.
No, I know it. There are frets, of course, but then do you have to, press 2 frets together like F chord on a guitar?
Yeah. So the strings are nylon, so they're soft and they don't really dig into your fingers. And like I said, you can play a chord with just one finger on a fret, or 2 fingers, or 3 fingers. But rarely do you have more than 3 fingers on the instrument at any time. So it's it's easy.
Let me show you what I mean.
Yeah.
So when you have this guitar, the problem with F is that you have to press the first fret with your next finger together, and then you have the normal one. And I have never actually mastered, pressing 2 frets with one finger. It's just way too much.
Oh, huh. Yeah, you can do 2 frets with one finger. So you just collapse your finger a little bit. That's the way I do it.
Yeah, but in the middle of your finger, it's very soft. So it's just it doesn't really press the way it does, and then it doesn't sound well. And it's all like,
you should try one of these. Way easier because the strings are soft and there's very little tension on them. So you don't have to press very hard. You barely press, and you get it down. So it's just easier than a guitar in a million ways.
Well, I have the classical one also with nylon strings, and it should have actually did the transfer learning, but then it doesn't actually work that way. Finally, Josh, what do you do to stay in shape? Why are you not bald and old and out of shape?
I love jogging. I go jogging all the time. Jogging is one of the things I do to think about or try to solve problems when I'm thinking about StatQuest. I'm stuck on like, what would make the best way to visualize this? What would be the best visualization? I just go for jogs, and I think about it while I'm jogging around the neighborhood. I figure it out. So I do a lot of jogging.
Wish you more jogging if that means that you are going to be having more wonderful neural network videos coming in.
Yeah.
Thank you so much, Josh, for your time. It was wonderful talking to you as always. And hopefully this new year is going to bring you all the happiness and prosperity, and it will be the year of your goals. Hope you hit your 1 million goal as soon as possible. And then we have a quadruple BAM coming, right?
That's right.
Okay, there they go.
Yeah.
All right. Thank you so much, everyone, for tuning in. This was Josh, the legendary Josh, and me. I'll see you again very soon. Thank you so much for tuning in, and see you again. Bye.
Thank you very much, Manoj. Thank you. Okay, bye.